Welcome! Today, we're diving deep, literally, into the secret life of lakes. We're going to explore the powerful, invisible forces that stir these massive bodies of water from top to bottom, and we'll find out exactly why that churning is so incredibly important.
And trust me, it matters a whole lot. This isn't just about water sloshing around. Think of this mixing as the lake's circulatory system. It's what carries life-giving oxygen from the surface down to the fish in the deep, dark depths. It dredges up essential nutrients from the bottom for algae to feast on up in the sunlit zones. It basically distributes life throughout the entire water column. The health of a lake's whole ecosystem? Yeah, it depends on this.
All right, let's get into it. Here's the plan for today. We'll start with the forces that drive all this mixing. Then, we'll look at the physics that resist it. After that, we'll take a trip through the 4 seasons to see how lakes change, and then use that knowledge to start classifying lakes, before we look at the full system and wrap it all up.
Okay, first things first, what are the actual engines driving all this activity? Let's take a look at the main forces that cause a lake to mix in the first place.
It really boils down to 3 main drivers. The big one, the most important by far, is wind. It creates friction on the lake's surface, literally dragging the water along. But you've also got inflowing water, from rivers and streams, that brings in new water with its own energy. And of course, water has to go somewhere, so outflowing water also helps to create currents and get things moving.
So if those forces were the only thing going on, you'd think lakes would just be constantly churning, right? Well, not so fast. There's a really powerful opposing force at play here, and it's called stratification. This is how a lake fights back against mixing. And this all comes down to a concept we call lake stability. All this means is, how good is a lake at resisting those mixing forces like the wind? And that ability to resist is controlled almost entirely by one thing: the difference in density between its layers of water. Scientists can actually put a number on this resistance. They use a metric called the Schmidt's Stability Index, or SSI for short. It's basically a calculation of how much energy, say from a big windstorm, it would take to completely break down those density layers and mix the entire lake into one uniform temperature. So you've got these 2 key states. On one hand, you have a stable lake. It has a huge density difference between its top and bottom layers, creating this super strong barrier that wind just can't break through easily. But an unstable lake, it has almost no density difference at all, which means even a gentle breeze can start to get the water turning over. So now let's see how these competing forces of mixing and stability play out in this beautiful, predictable cycle that's driven entirely by the changing seasons and how they affect water temperature.
So, when a lake is stable, or what we call stratified, it settles into 3 distinct layers. Up top, you've got the Epilimnion. It's warm, it's full of light, and it's mixed by the wind. Way down at the bottom is the Hypolimnion. It's cold, super dense, dark, and totally undisturbed. And that zone in the middle? That's the Metalimnion, where the temperature just plummets. That sharpest point of change has a special name, the thermocline.
This whole annual rhythm is this amazing dance of temperature and density. Let's start in winter. The lake is what we call inversely stratified. Ice at 0 degrees Celsius is floating on top of the densest water, which is actually at 4 degrees Celsius, sitting at the bottom. Then spring comes. The ice melts, the surface warms up to that magic 4-degree mark, and suddenly the whole lake is one uniform density. Now, the wind can go to work, mixing it top to bottom in an event called turnover. This is huge. It brings up all those deep water nutrients, sometimes causing massive algae blooms. Summer brings that strong layering again, but as the air cools in the fall, the surface water cools back down to 4 degrees. Density equalizes, and bam, you get another complete turnover. Okay, now that we have that seasonal cycle down, we can actually start to classify different types of lakes based on how and how often they go through these mixing patterns.
The vast majority of lakes on our planet fall into this first major category. They are called holomictic. It's a fancy word, but it just means the whole lake, holo, mixes, mictic, at least one time every single year.
So within that big group, we have the monomictic lakes. Mono means one, so they mix just once a year. You have cold monomictic lakes, usually way up in polar regions. They're frozen most of the year and get one brief mixing window in the summer. The opposite is warm monomictic lakes. They never freeze, they stay layered all summer, and they only get to mix during the coldest part of the winter.
And then you have the classic textbook example, Dimictic lakes. Di means two. These are the lakes that follow that perfect seasonal cycle we just walked through, mixing twice a year. They have that spring turnover, they stratify in the summer, they have the fall turnover, and then they're inversely stratified under ice all winter.
All right, so beyond those really common types, there's this whole other fascinating spectrum of mixing behaviors that we see in lakes all around the world. Polymictic lakes are kind of the opposite of stable. Poly means many. Because these lakes are shallow, it doesn't take much wind to overcome any weak layers that try to form. So what happens? They just mix constantly, frequently, and often pretty irregularly all year long.
And we can break this category down even more into 4 subtypes, based on whether they have ice and how long any layering actually lasts. So at one end, you have a continuous warm polymictic lake. Just picture a shallow pond in the tropics. No ice, and it mixes pretty much every day. At the other end, you have a discontinuous cold lake. It's got ice for part of the year and can actually stay stratified for a few weeks at a time in between these random mixing events.
Finally, we get to the really rare ones, Oligomictic lakes. These are often super deep and in the tropics, and they're so stable they might only mix once every few years, or even less. And then, the most extreme of all, Meromictic lakes. These lakes are permanently stratified. Something, usually a whole bunch of dissolved salt, makes that bottom layer so dense that it never, ever mixes with the water above it. This creates this spooky, oxygen-free zone at the bottom of the lake, forever.
So that was a pretty fast tour through the physics of lakes. Let's just do a quick recap to pull all of these different classifications together. This chart really helps organize everything. All lakes can be put into these categories. You have the holomictic lakes that mix all the way down, and those are broken up by frequency. Polymictic is many times, dimictic is twice, and monomictic is once a year. Then you have the lakes that don't mix fully. That includes the oligomictic, which mix very rarely, and the meromictic, which are permanently layered and never mix completely.
So at the end of the day, these different classifications give us an incredibly powerful framework. They help us understand the fundamental physical engine that drives the ecology, the actual life, of pretty much every single lake on this planet.
And that brings us to a final and really important question. You see, these classifications are deeply connected to climate. So what happens in a world that's getting warmer? How might a classic dimictic lake, one that relies on a cold winter to form ice, how might it behave if those winters just aren't cold enough anymore? Could it actually shift and become a monomictic lake? It's a critical question to think about. Thanks so much for joining this explainer.